let's see, before we get started, so Colton emailed and said that he wanted me to do a couple of the problems on this worksheet. We'll do that in a minute. Let me see, do I have this PowerPoint up still? Maybe I don't. Yeah, there it is. Okay, good. There we go. So there it is. So tomorrow is our, oh, put this down. So natural and social sciences, awards gem. Now, if you're thinking, I'm not part of the natural and social sciences, well, then you can go to a different gem. And you whatever it is, I don't know, with education people or, so some of you have decided to do it on a different day. And I think you have to go on Friday?
Well, I go to the awards chapel, but I want to go to chapel.
Oh, you want to go to the real chapel?
Yeah.
Oh, why is that? Because it's Pastor Stephanie's?
Well, not necessarily, no. But no, my friend is going to be the chapel band leader next year.
Yeah.
And
Genesis?
well, no, she's leaving, but like each leading a song on Friday, and like it's like passing around the torch. I know I want to go to the but I can't.
Well, you could.
Because I have the awards.
Are you getting an award?
I don't know, maybe.
Yeah.
I don't know.
Yeah. That's a tough thing.
And I don't want to not.
Yeah, I know. Yeah, I know everyone who's getting an award at this. So, but I won't tell you. Sorry, I've been sworn to secrecy. What? I'll let you know on. I'll let you know. Yeah. Yeah. If you get an award and you skip, I'll make sure I'll bring your award on Friday. That's it. Okay, so here we go. What? No. Well, I neither confirm nor deny any of this. Okay, so wait, you're not. Oh yeah, you're education. Well, I don't know. Some people are like both education and math. Okay, so let's see. I know number 11 was one that Colton wanted to look at. So maybe we should just take a look at that right now, especially because it's a definite integral. That makes it extra fun. Yeah, let's do it. All right, so take a look at 11. So we're doing worksheets. I guess it's homework worksheet homework. So number 11. If you have it, if you don't have the worksheet, there's number 11. So first things first, I think we all can guess what u is going to be, right? Like it's the thing in parentheses. So let's do it. Let's try that. U is equal to radical x plus 1. And the derivative of u, I'm going to be a little bit more careful with this. It's 1/2 x to the negative 1/2 because this is x to the 1/2 plus 1. So I think, oh, du, dx. Does that look all right? Just want to double check. That's the first step. If you don't get that step, then yeah, you're going to be stuck. The rest of it's not going to make any sense. So if that looks good, then let me just rearrange this slightly. And I totally realize that some of you want to do your algebra a little different than the way I do my algebra, but honestly, it's just that one algebraic step that is different. If you prefer a different way, it's not really a different way. It's all the same to do integration by parts. Anyway, so I'm going to do it this way. We've got radical x plus 1 squared, and then times 1 over radical x dx. So that's my first step. I don't want to do things too quickly, so that's why I'm kind of dragging this out. Oh, I forgot my limits. 1 to 4. Now I need this 2 here, so notice that there's a 2 down here. So I want to put a 2 right there, but in order to balance things, I'm going to have to put either a 2 up here or somewhere else. So I want to balance this 2. Let me go ahead and draw this in blue. So that 2 there is going to balance with that 2. Notice that those cancel. So I haven't added anything. I mean, I know I've put a 2 there, but so now this looks exactly like this dx here, or du. So now I can actually do the substitution. So this becomes 2 times the integral of 1 over u squared du. Let me pause for a minute because that might be a little bit much. Don't want to blow your mind too much. All right, yeah, what do you think, Kevin? I get, I made, so wait, which line? Make sure I get the right, here, let's number these. This is line 1, here's line 2, and here's line 3. So is it line 3? How'd you get line 3? Okay, just want to be sure because there's stuff went on before the line 3. So what I did was I first of all noted that this stuff here is the same as this stuff here. So take note of that first. So you see how those are exactly the same? And so because those are the same, it allowed me to replace them with du. So that's the first thing that you might notice. The other thing that I did was I noted that this stuff down here is the same as this stuff here. And so that allowed me to replace that with u. So those are the two replacements I made. I just made substitutions. That's the crucial step. Once you have your substitution, now this is so much that I don't even know what that is. I don't know how to do that, but I know how to do this. In fact, you guys all know how to do this. This one's easy down here. So let's just go ahead and do it. That's going to equal 2, I guess, negative 2 times u to the negative first. Well, let's not put a plus c there. So you might wonder, what did I just do? Well, I in my head, which if you can't do it in your head, it's fine. In my head, I thought of this as u to the negative 2. And then I thought of the antiderivative of u to the negative 2. You add 1 to the power and then divide by that power. So you add 1, you get negative 1. That's where this u to the negative 1 came from. And then I've got to divide by negative 1, but I just wrote it as negative 2 because there's the 2 there. So it could be 2 over negative 1. There it is. I'm leaving off the plus c because this is a definite integral. So when I change back to x, I'm going to plug in the limits. One thing to make note of is that these limits are values of x. X equals 1, x equals 4. They're values of x. They are not values of u. So that's why I've got to switch back to x before plugging those in. There's another way of dealing with limits, but I'm going to keep that a secret. I know that makes you all want to learn it all the more, but sorry. Maybe next semester if you're with me. Okay, so I'm going to switch back to x. So notice that I'm just taking the u, sticking there. And now that I'm in the land of x, I can put my limits back. And that's what it looks like. Look all right? Now plug and chug and we're done. So let's plug it in. So it's going to be negative 2 times the square root of 4 plus 1 minus negative 2 times radical 1 plus 1. Okay, there's a little bit of sorting that has to happen here. So we got to deal with this. It's going to be negative 2 over 3. Is that right? Because radical 4 is 2 plus 1, 3. But the negative 1 there means it goes in the bottom. Do the same thing over here. I've got plus 2 over 2. Oh, that's easy enough. So I guess 1/3. That's my final answer. Let me zoom out a bit so you can see the entire joyful problem and ask whatever question you need. Yeah? You look like you're angry.
So, I kept it as, I got 2 over u squared.
Yep.
I got negative.
Yeah, that's because you left out a negative somewhere.
Oh, did I? Is that technically correct?
No, no.
Obviously not the 1/3. orientation.
Okay, so you're saying right here at step 3, you did this.
Yep.
And that's equal to -2 over u to the negative first. Is it the negative, that negative is the one that you left out?
Yes.
Oh, sorry. That negative there, sorry, this negative there.
It should be 2 there.
Yeah, there we go. There it is, good. Anything else, other complaints, concerns?
Can we please go over 10, 9, and 12?
Okay. 10, 9, and 12. All right, yeah, 10 is also on Colton's list, so he's going to be overjoyed with that one. So let's take a look at 10 first. Then we'll go back, do 9 and 12. And 9's down there. Where is 10? 10 is this one. All right, yeah, so let me just blow through this kind of quickly, but I'll pause it at some key moments. So first of all, u, I think we'd all probably see that this is going to be e to the 2x plus 1. The stuff in the parentheses. Du, the derivative, is 2e to the 2x dx. Double check that. It's using the chain rule. I should label these things, shouldn't I? Chain rule. I'm going to erase some of this stuff down here. We don't need it anymore. We've already had fun with that stuff, so we don't need it. Okay, so we got that. Now let's go ahead and see what we need to do over here. I would like to put the e to the 2x over here next to dx, because you'll notice that that's what it looks like over here. And then I need a 2, so I'm going to just stick the 2 here and multiply this by 1/2. So once again, it looks like magic, but hopefully you're getting used to my magic. It's not that magical, is it? It's algebra. You're just multiplying by 1. Now I can do my substitution, so I'll pause after oh no, get rid of those limits because we're changing to u. So we've got 1/2. This thing becomes u to the 4th, and all of that stuff at the end becomes du. So check it out. Yeah, Gavin?
So, where do you put 2
Out of,
you just add those to cancel it?
I wanted, okay, so here's the thought process is I would like to see this. I want this, and I didn't have, before I did that, I had this. So what I'm missing is I'm missing the 2. And so to get the 2, I multiply by 2 over 2, because 2 over 2 is 1. That's legal. You can multiply by pi over pi, 7 over 7, anything over anything, as long as it's the same thing. And then I took the one on the bottom 2, I moved it out here. And so it's all, everything's legal. Everything's legal. And now let me just make this look a little bit better. So that the whole goal was to make that dx look like whatever I got there. Whatever I've got for du, I want to see. So that I can make a direct substitution without any like, it has to, I guess the reason why I like doing it this way is because there's no margin for error. If you're forced to make your equation look like the du, then you can't, there's no guesswork. It's like, yeah, it's got to look like that. And if it doesn't, then you can't do the substitution. Jarrett, what do you think?
What?
I don't know. You had your hand up a minute ago.
I did, but
And then you changed your mind. I love it when you do that. That's my favorite. All right, so good. So far. Yeah, all right, almost there. Now that we got this, the rest of this is pretty straightforward. We're going to get u to the 4th. The antiderivative is u to the 5th over 5. So we've got u to the 5th, and then I'm going to put the 5 with the 2 over here. This thing is a definite integral, so I'm not going to put a plus c on it. And so now I'm going to put my x back in here, e to the 2x plus 1. That came from this. And I can put in my limits. Oh, x to x equals natural log of 2. And now it's just some arithmetic. We have e to the 2 times natural log of 2 plus 1 minus 1/10 times e to the 2 times 0. What? Oh, fifth power, thank you. Oh yeah, there, I left it off here. Thank you, the fifth power. Sorry, I was so excited about natural log of 2 that I forgot about my power. Thank you. Okay, so we're almost there. So this is going to be 1/10 times e to the 2 times natural log of 2 is 4. Plus 1 to the 5th minus 1/10 times e to the 2 times 0 is 1. 1 plus 1 is 2. So let's see, that's 5 to the 5th. 3125? 3125? 125. And 2 to the 5th is 32 all over 10. So whatever that is, it's going to be 30, 90, 2, 3, 10. So 309.3 apparently. Very nice. No? I don't know. You got a negative again?
No.
Did you plug in this correctly here?
I got the right form. I'm just going to write down your answer and hopefully you get it.
Okay, that's fine. You can just, I mean, you can all hang on to this. It's fine. Going over what we can. Yeah, I just want to make sure we have some ample experience with this substitution method. It's super important. This is so useful.
Would you consider this to be a substitution problem?
This one?
Yes.
Yeah, probably on the easier side. Not the easiest. I mean, this one is probably no, that one's kind of special because of the X out front. Let's see, where's the easy? That's pretty easy. Yeah, the ones where you don't have to do much to get the substitution done.
True.
Oh yeah, that one. Well, that one you have to recognize that the arctan derivative of arctan is 1 over 1 plus t squared. Yeah. So. Okay. Wait, someone said 9. Okay, well we can do 8. We can do it. Yeah, this one's super quick. Arctan. Okay, so this one violates my my rule of thumb. I think I said something like 95% or 98% of the time you use the thing in parentheses. This one you don't, because if anything, 1 plus t squared is implicitly in parentheses. However, the derivative of 1 over 1 plus t squared is not somewhere. So arctan of t, though, there is a derivative of that. The derivative of arctan is 1 over 1 plus t squared, which we all know and love. And so once you see that, then it's like, oh yeah, it's right there. Let me just rearrange this so it's super obvious. Arctan of t, there's no math magic involved here. This is all just manipulating algebraically, moving things around so that you have that. And now you can see, oh, it's hopefully pretty obvious that this here is going to be du. That's going to be u. So I've got the integral of u du. And yeah, almost nothing to do. Then we do 1/2 u squared. And now I'm going to put t back in there. So that's going to be 1/2 arctan of t squared evaluated from t equals 0 to 1. Now we all know what the arctangent of 1 is, so I won't belabor it. It's pi over 4. And we all know what the arctangent of 0 is. It's 0. So this ends up being pi squared over 32 when you get done with all the arithmetic. So I know I did that a little quick, but really it's this step right here that is the crucial step. So if I had written number 8 like that in the box, I'm sure that it would pose no problems whatsoever. So if I put that on an exam on Friday, that's a great one to have on the exam, I think. In fact, I'm going to have to make note of this. Where's my notes? I made notes yesterday. Differential equations. My differential equations people had a whole list of things they wanted me to do. I've done one of the things that they had on their list. So let's see, this is number 8. Stick it on the test. How's that? So now you know at least one thing that's going to be on the test on Friday. All right. Yeah. Well, I can always pull it out aggressively too and add more to it. Okay. So there's number, let's take a look at number 9. Anything left on number 8? Now, number 9 is also super easy. I know it doesn't look like it, but check it out. It is amazing how simple number 9 ends up being once you choose the correct substitution. So here again, it may not be obvious. So let me put in a set of parentheses here. And if you use that thing for u, sine of x squared, and apply the chain rule, then you get, let's see, cosine of x squared. Derivative of sine of x squared is cosine of x squared times the derivative of x squared, which is 2x. Oh, how convenient. It's right there. So all the algebra that you need to do, if any, is just to swap these two. Move the e to the sine of x squared over there and put the 2x cosine, x squared dx together so that it can make this substitution. And that's, yeah, look at it, it's almost done. Basically here, e to the u, which in this case is e to the sine of x squared. Now, the next step is not that kind or fun, but you know, you have calculators. And I'm just going to box that. So, if you want to punch it into your calculator, you can. But, no, we're not going to turn this in. Yeah, because I want to make sure you, well, partly because I still have a stack in my office. I need to bring the accordion tomorrow because I know some of you want your stuff. So I'll bring that along with whatever I can shove in it from the stack. And I just don't want to add to the stack at this point. Yeah, Jackson? There. Is that enough of it? Does it look all right?
So why is sine of x squared u?
Okay. No, this is a great question that Jackson asks. Why is it that sine of x squared is u and not just x squared? And here's the answer: it's just preference. You could make x squared u, and that would work. In fact, let's back up. Let me make sure. Is everyone happy with what I got here? You've written down what you want to. You could always revisit the magic on the video later today. As long as you go to the live tab. Remember, go to live tab, not the, anyway. So if you're okay with it, I'm going to erase this, and I'm going to do the Jackson method. So I'm going to close. Yes, that's right. That's the only, so I like this method though. I like what Jackson's suggesting because it is in some ways simpler, and in other ways it's more complicated. So it's like you choose where you want to complicate your life. But no, this is great. Yeah, thanks for bringing this up. I get it in my head that I have to do it a certain way, and then but anyway, Jackson, what would your du be if you're going to choose u to be x squared? Yeah, 2x dx. Okay, yes, so this ends up being this. So we have the cosine of x squared e to the sine of x squared times 2x dx. Now I'm just going to rearrange it the way Jackson wants me to with 2x dx at the end. And then this stuff becomes du. I have cosine of u e to the sine of u du. What's that? Well, I will eventually.
But can you do it in this step?
No, I'm going to do another substitution. That's the complication. No, you could. Yeah, you probably can see, oh, I know what the antiderivative of this is. And if you do, yeah, you're done. But if you don't, then you have to do another substitution. So now at this stage, I need a second substitution. And it doesn't seem good to use u for my second substitution because I've already got a u there. So since it's a double substitution, maybe I'll use double u. Okay, I know. That's a really poor math. What's that? It's like a dad math joke. Okay, w. W. So my w is going to be sine of u, and dw will be cosine of single u du. There you go. So anyway, that's the deal. I mean, the rest of this is almost exactly like the previous one, but let me just might as well finish it up here. This is e to the w dw, which ends up equaling e to the w, which ends up equaling e to the sine of u, which ends up equaling e to the sine of x squared. So you end up getting the same thing, but I have to go through two substitutions instead of one. But there's nothing wrong with that. It happens.
You didn't have to do the second substitution.
What?
You didn't have to do the second one because it was clear that.
Okay, but then you're doing it in your head. You're doing the reason why you end up doing two substitutions or you have to do two of something is because there are two chain rules. Like if you do the derivative of this, you have to do chain rule twice. So that's why there's two different possible substitutions. So if I was really mean, I'd have one with three substitutions, but I'm not going to do that. That'd be too much. Bonus. Triple sub bonus. Was it someone in here? I don't think it was someone in here. Someone, I think it was in Calc2, was complaining to me that I didn't offer bonus points for doing the end of course survey like some other professors. And I said, well, that's because those other professors are wrong. It's bad practice to do that. I'm happy to do bonus points for things that are actually course material related. But the end of course survey, that's just related to my job. And honestly, at this point in my career, you can give me ones, but I prefer fives. So give me some fives at the end if you want, that makes me feel good. But you can also write notes to me. I've had people comment on my shoes before. I don't know why. You can comment on the ties, whatever. Yeah, put some comments in there. It's fun. I love the comments. Honestly, I look through the numbers. I'm like, a bunch of, it's usually in the fours, like when you average everyone, because you got a bunch of people that like me, and then a few that don't, and it all averages together. But anyway, getting back to this, why did I even mention that? I don't even know. The end of course survey. Oh, extra credit, bonus, yes. Yeah, I actually had someone just on Monday complain that I wasn't going to give bonuses. They're like, can't you give bonuses? This other professor does. I was like, yeah, that's not right. I mean, yeah, it's not. Yeah, well, okay. Still not right.
Yeah, that's what I'm saying.
Yeah, then everyone gets the rising tide lifts all boats, right? Well, anyway. What? There is no tenure here. I'm as close to tenure as you can get. So, yes.
So what is that?
I get every 5 years, they look at me and they say, if we fire you, we got to hire someone else. And so they keep me and they give me another 5 years. In fact, that just happened. So I've got another 5 years, which means I'll be 59. And then I'll get another 5 and then I'll retire after that. So. Okay, so what is this? What's that? Huh?
You're younger than my dad.
Seriously?
Yeah. And it's 56.
That's weird.
I feel strange.
Yeah, because
My dad's 42.
yeah, I used to be younger than everyone's dad, and then I became older because all my kids, my youngest is graduating from college in 3 weeks.
I am the youngest, but my brother's 20.
Okay. Well, my oldest is 26 though. My oldest daughter. I can't even imagine being like this old and having a teenager still. I mean, it's rough. All right, what are we doing? Oh, number 12. 12, and then we'll be happy? All right, let's do it.
12 is annoying.
T squared plus 4 is u. That means that du is going to be 2t dt. Good enough? Okay, so here's the problem with number 2, or number 12, is when I try to separate things out, I get this. Let me explain after I get done moving. So what I'm looking at here is I'm looking at this in particular. I know there's a 2 there. The 2, we can easily deal with the 2, but it's that t dt. I want to get that first off. But when I do that, I've left behind this 3t squared. It's like, what's going on with the 3t squared now? Well, we'll get there. Anyway, let's deal with the 2. The 2 is easy. You've gotten used to this. As long as you put a 1/2 and a 2 like multiplied, it's all good. So now that's good, but that t squared is still there. So what I got to do is I got to take this thing and rearrange it. T squared is equal to u minus 4. Okay, so now I've got 3 substitutions I've got to do, but it's okay. We've done this before. I think number 7 had this. So let's do this here. It's not that bad. So we've got 1/2 times the integral of 3 times u minus 4. So that's that first, or the squiggly one arrow. And then this stuff is going to become u to the 5th. And then this last stuff is just du. So that is there, this is here, and that is there. So check it out, make sure it makes sense. So I like Jared's analysis of this one. It's just annoying. It is just annoying, isn't it? But there it is. Now that we've got it like this, it's pretty straightforward. Let me write it again with some algebra. U to the 6th minus 4u to the 5th. There it is. Look all right. Now you can go ahead and do your, your stuff. This is 3/2 times u to the 7th over 7, 4u to the 6th over 6. Okay, double check my antiderivative. Oh, plus c. Sorry, I got used to having a definite integral, and this is an indefinite integral, so I have a plus c. And then finally, we can just make our substitution. I'm only going to use this U right here. Let's do that. So, and I think I'll multiply through by 3/2 as well. 3 times, what was my U? T squared plus 4, 7 over 14. And then the 3 times 4 is 12, divided by 6 is 2. And then the 2 cancels with the 2 there. So this is just going to be t squared plus 4 to the 6th. Let's see. Yeah, because all of this, the 4/6 and the 3/2, when you multiply, you get 12 over 12.
U.
What's wrong? U? EU? Oh, EU. Oh, I thought you were coming up with a new substitution. We could have EU.
Do a third variable for the substitution. Not.
Oh, you mean
not
it's
like
3
the step-
substitutions?
Not like the step that we did last time where we substituted something for an arc substitution. We're talking about adding another variant.
You mean sort of like what we did here? This is up here, you have this and
Yes,
this,
Not in terms of,
not in terms of U?
yeah. Would you be allowed to do that? Or is there no-
If you're using correct algebra, but I'm not sure that I can envision a reason why. But as long as you're following the rules of algebra and you're not making things up out of whole cloth, you can do whatever you want. So, and you don't. Here's the crucial step though, is this right here. Is when you get done substituting, you should only have a single variable there. You shouldn't have any t's, just u's, or w's, or u's. Whatever you want to put there is fine. That was rough, wasn't it? Actually, it wasn't that bad. I
As
liked
long
it.
as there's not one like,
None like 12. Done.
Thank you, Dr. Mann.
I got it. I still haven't printed it. That's why I can do this. Tomorrow it'll be too late. So get in your request now. Let's see. Oh,
I think there's
wait.
going to be one question.
One
It's really difficult.
answer should be 2. You say you want one of the answers to be equal to 2?
No, I want one of the questions to be what's 2 plus 2.
No, that's too easy. But I'll have one answer. I made a test once.
Can one of the questions be what's the quadratic formula?
No, sorry. But I made a test once where I thought it would be funny if every single answer was the number 2. And exactly, that's what happened is I gave it, like about midway through, I had people coming up to me, is this okay? Yeah, it's okay. So, yeah, what I should have done is I should have had all the answers to except for one of them, which was 3. That would have been mean. I wouldn't do that. So, but at least one of your answers will be 2, so you can look forward to that. Got it on the list. Okay, Jackson, what are you requesting?
Can we not do anything like arc tangent or arc sine?
Hey, he just voted.
They're my favorite. Yeah, actually, it's impossible because that would contradict my first thing, which is that number 8 will be on the test.
So is
You can only do one question
being
and
on
I'll
this
make it
list?
hard.
So how about this? Yeah,
Will it be
I will.
exactly the same?
I will go through the list and I will apply the rules in order. So then I have the rule: no arctan, arc sine, but the no arctan arc sine comes after 8 is on the test. So 8 goes on the test, and then after that, so anything other than 8, no arctan arc sine. How's that?
Or cosine or secant.
Yeah, same thing. Arc anything. All right, yeah, enough of that. What else from here? Do we have any other issues?
And then there's a bonus question about you, like what's arctic color?
It's ridiculous. No. No, that's not related to the course. Okay, so we need to move on. We have, what?
In my opinion, I like that.
Yes, so let's talk about the net change theorem just briefly. Let me find, just a minute, let me find this. Hold on a sec. I hope I can find it. Give me a minute here. Should have found it earlier. Classes, yeah, we'll talk more. Once tomorrow, I'll have the thing all typed up, sent to the printer, so I can even show you, but this will help me as I finish it up. Drop anything? Okay, so let's see. What was I looking for? Net change theorem. Where did I put it? Here, just a minute. It'll be easier if I look on my computer. Here. I don't know where my net change theorem ended up. If I can't find it, then I guess we're not going to do it. Would like to have a. Oh, here it is. Yeah, I know. No, this is easy. So we're not going to do parts. So so here, this is it. Net change theorem. I know it says quiz at the top. It's not really a quiz. So I just wanted to have structure to use. Yeah, so we're going to skip parts, but parts is the first thing that we do in Calc 2. So if you do Calc 2, we'll do parts. Parts is doing the product rule in reverse, just like substitution is doing the chain rule in reverse. But anyway, let's talk about the South Cascade Glacier in Washington State. It happens to be shrinking at this rate, where a certain number of tons per year, where T is measured in years beginning in 1950. So here's the thing with the net change theorem. Net change theorem says that the net change of something, whatever it is that we're measuring, is always going to be the definite integral of the rate. Rate. dt, or whatever it is. In this case, it's dt. This is the same as what we did when we were talking about distance. If you have someone moving and you know their velocity, you can integrate their velocity to determine how far they have moved. So net change, how far have you gone, is related to the rate. Okay, so net change is rate. So we're going to do this with this particular glacier. So that's the glacier there. So this is going to be the integral of 1,000 minus t plus 0.1 t squared. And this works with anything. I picked a glacier here just because, well, it was in my files, but also that's different from other things. You can imagine a rate of a reaction, like a rate at which some chemicals are combining or whatever, and you could talk about the net amount over time that you've, or you have the rate at which a population is growing, and you could talk about the amount, the net amount of increase that you have over time. So this is the same thing here. How much is the South Cascade Glacier shrinking between 1975 and 2000? And T is measured in years beginning 1950. So 1975 is T equals 25, and this is T equals 50. So 25 to 50. So how much ice was shed off of this glacier during those 25 years? If in fact this was a correct model, which I'm sure it's not, because I made it up. But you could imagine this. Oh, I should have had you do this. Yeah, do the antiderivative. I've already started it. It's good practice to double check that you know how to do the antiderivative. All right, so you've got your antiderivative, I hope. It's going to be 1/2 t squared plus 0.1 over 3 t cubed. Is that all right if I write it that way? Guess it's going to have to be. Okay, so next we're going to do plug in. So that's going to be 50,000 minus 1250 plus, it's going to be 125, just a minute, 50 to the third is 125,000, 00, so that would be like this, I hope. I guess someone with a calculator can check. So it's, I'm doing 50 cubed times 0.1. I think that's right. Yeah, that should be right. Anyway, so subtract off. Oh, this one's going to be harder, isn't it? 25,000. Okay, 25 squared is 625 divided by 2. I don't know. So I'll just write it like that. 25 cubed is too much for me to think about at this point. It's 625 squared. What is it? Oh, I see. That's 625 divided by 2.
Yeah.
I was doing doing the next term. I'm just going to write it as 25 cubed times 0.1 over 3. Now we can use our calculators. You probably could have used them at the very beginning and been happy about it. So take a minute and do that while I write the next problem down. It involves the net change theorem. All right, let's see how we did. Did anyone get this on their calculator? I'm just curious what the final answer is. I mean, oh wait, what was that? Oh, is that the final answer for the whole thing? I feel like it should be sixths. That's with everything.
It might simplify.
It might, but it shouldn't. Maybe it does. No, yeah, okay, maybe, okay, I believe it now. Whatever, I'm okay. Yeah, it's some big number is important. 83, 125 thirds. Good enough? Okay, so yeah, so that's the amount, the total amount of ice that has melted from this glacier, if my model was correct. So tons. Okay, related to this is this idea that if we know the beginning point, so we have the net change, so think of net change as being how far I've moved. So if I do the integral, let's say I know my velocity as I move around, as I wander around, and I'm going back and forth or what have you. And if I know where I started, then I can say where I'm going to be at any given moment. If I don't know where I started, then I just know how far I've traveled. And so like here, for example, this tells me how much has melted, but it doesn't tell me how big the glacier is at any given. I mean, that might be just a drop in the bucket. I don't know. So here's the idea, is that if you have something like velocity, then you have a starting point, then you can use this net change theorem to figure out where you are at any given moment. In particular, here's the idea, is that S of t is going to be the integral from 0 to t. Oh, let's not do it that way. There's a formula, but that's scary. Let's just do the antiderivative. Let's do it that way. S of t is the antiderivative of v of t. Yeah, that's going to be a lot easier to comprehend. There is some notation that I was about to use, and then I changed my mind because I thought, nope, don't want to confuse you. This makes sense though. If the derivative of position is velocity, oh, I should mention this is position, velocity. Remember day one? It's like day one. We're dropping watermelons off the top of Raston Tower. So yeah, I got this velocity and position thing. So you can do this. What's that antiderivative of velocity? Oh, I'll write it here. 3t squared minus 3. So we can do this, right? 3t squared, that's an easy one. So easy that no one wants to do it. It's t cubed, right? Yeah, t cubed. And then minus, this is 3t. All right, this is easy. Okay, so there's one thing missing though, right? It's the plus c. So we've just been using the plus c as a placeholder, saying, yeah, there's a plus c, whatever. But the plus c has meaning, and it's related to the net change theorem, this idea that the integral of the velocity is the amount that you have moved, or the integral of a rate is the amount that something has changed, the net change. So anyway, down here, the c is related to that in the sense that if we know the starting point, then we can say what this c is and predict how far we've moved at any given moment. So that's the idea behind the relationship between the net change theorem and this. There is a formula that would make it a little bit more clear that this is directly related to the net change theorem, but I don't want to introduce that notation, so I'd rather just think of it this way, that we have s of 0 equals 5. So we have, first of all, s of t is t cubed minus 3t plus c. S of 0 is equal to 5. What I'm going to do is I'm just going to plug that in. S of 0 is 0 cubed minus 3 times 0 plus c. So that means 5 has to equal c. C is oftentimes going to be that S of 0, the initial position. Not always though. Just want to warn you about that. Depending on what function you have, you might have c be something else. So anyway, there's c, which means that my position is t cubed minus 3t plus 5. So that c is actually 5. So that tells me my position as I'm wandering around, and I can predict where I am at any given moment now. So how far have you moved at any moment in time? What do you think, Jackson? So I took this. So yeah, I'll do it slowly now. So this was given to me. So that's something that was given to me. I'm told that this is where I'm starting. I'm starting, let's see. Here's the wall. I'm starting 5 meters. 1, 2, 3, 4, 5. About there. So I'm starting 5 meters from the wall, and I'm moving according to that velocity. So that's sort of what's happening. I'm starting right here, and I'm moving. And so I want to know where I am at any given moment. So when I do the integral, the definite integral, I get the plus c. And that tells me that this is here. So this is where I am after the definite integral. So you're probably fine with that, because we've been doing that. We throw the plus c on there. So the net change theorem just helps me to figure out what the c is in this given moment. So I'm standing here at the beginning of my little walk as I start wandering. Maybe I walk that way first. Yeah, I think I do walk that way first, because my velocity starts out being -3. So I start going this way, and then I turn around and I start going this way. But anyway, getting back to what's going on here, S of 0, my starting point is 5. So basically, I just want to pick, well, there it is. I want to pick the value of c that will make this here true. And so what I did was I just plugged 0 in, because this is S of 0 is 0 cubed minus 3 times 0 plus the c that we had here. And then I said, hey, wait a minute. This S of 0 is 5, and that's where this 5 came from. And of course, all those zeros are just 0. So this is because of the thing in the box up there. And then the plus c is because of the net change theorem. Yeah, so I just solved for c. And then when you get done, put it all together, and there's my position. Oh, it's time. Time to go. Thanks for enduring. Lovely semester. And, well, we're not quite done, are we? We still have tomorrow and Friday and next Monday, and then finals.
Would we not be able to do parts on
we could. Yeah, and well, it could be like bonus material, kind of like the spur of the tube back there somewhere. It's still there. Yeah, we can do parts. It's not hard. It's just the product rule. All right, I'm gonna stop the video in case you need to chat about some secret thing. Stop.